We are going to begin Unit 2 today, which is on chemistry. And it's going to be about the chemistry necessary for us to understand life that we're talking about. So, if we're talking about chemistry, it's kind of one level underneath biology. And we're going to start with what are atoms in section 1. So, atoms are the basic structural units of elements. I know when we think of atoms, we often think of some kind of nucleus, and then you think of these orbitals going around it, right? Okay, it's not quite like that, but I know that's usually what you're picturing in your head, okay? The term actually comes from a Greek guy, Democritus, who theorized the idea of an indivisible particle he called atomos. And the word atomos here means indivisible, is actually what it means. But that's where the term comes from. So, if we're talking about atoms being the structural units of elements, what are elements? Well, these are substances that cannot be separated into simpler substances. Okay, so an atom is, your single indivisible unit, even though we'll talk about how it is divisible. There are parts underneath it. But an element, okay, is made up of atoms, okay? So they cannot be separated into simpler substances. So when we think of things, we're thinking of things like iron, lead, oxygen, nitrogen, hydrogen, okay, things like that. You can't break those down into anything simpler without creating something else. Okay, so as it says right here, right, we cannot be converted into another substance by ordinary chemical reactions. Okay, we can't go converting oxygen into nitrogen. We have to do some pretty extraordinary things to do that. Okay, so an atom is the smallest unit of an element, and each atom retains all the chemical properties of that element. So we're going to see here that if something has 8 protons, which we'll abbreviate like that, it's going to behave like oxygen. Okay, and if you change the number of protons, it's no longer oxygen, it's something else. Okay, so it retains all the properties of oxygen so long as it's got, 8 protons, or 7 protons if it's nitrogen, and stays that way. There are about 90 elements that occur naturally, and if you don't have one on your iPad, I would suggest, just for the sake of having one on there, downloading a periodic table. You'll use it this year in biology class, and you're certainly going to use it next year in chemistry, so having that handy will be helpful to you. But about 90 of the elements on that table occur naturally. Right now we have up to 118, and we'll get more specifics when you take chemistry as to like what's natural, what's not natural, and why that might be. Each has its own 2-letter abbreviation called its atomic symbol, 1 or 2-letter. It should say 1 or 2-letter symbol. Okay, 1 or 2-letter abbreviation. Okay, called its atomic symbol. So, for instance, if you go look at your periodic table that you hopefully just downloaded, you'll see that carbon, which is element 6, has just got a single capital C. If you go look down at element 82, you'll find lead. Its symbol is Pb. So don't just assume that it's the first couple of letters or the first letter of the element is its symbol. Right. Some of these are named after the Latin names. Lead, for instance, is named for plumbum, okay, which was the Latin name for lead. Okay, and things like sodium, if you look at element 11, okay, its symbol is Na, which was the Latin for natrium. So just because you know the name of an element, don't assume you know its atomic symbol. Most elements exist in small quantities in nature because they are part of compounds and ores. Most things are already reacted. And when you take chemistry as a sophomore, you'll understand why that is the case. Okay, so it's not common for you to just go digging in your backyard and say, find a giant hunk of lead. Okay, that's not a common thing. Most of that stuff is locked up into ores, and you have to refine it. Every once in a while, you might get lucky and find some natural deposit of a particular element, and that's where mines exist. But even mines have to deal with ores oftentimes. So most of the time, you're not going to go digging in your backyard and find like a hunk of aluminum or certainly not sodium or anything like that. Most of it has already reacted. And only a few elements are essential to life on Earth. We're going to see what those are here in a second. But even though there are 90 of them that naturally occur, there's really not that many that we need to use to live. So as I was saying just a moment ago, you don't need every one of the 90 elements to live, at least as a human. And some forms of life need even less than what we've got. But if we take a look over here, this table or something very similar is in your textbook. All right, we'll talk about what these atomic numbers and mass numbers are here in a few minutes. But just so you can see, here are some of the things that are necessary for us to survive as humans. Okay, oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iron, fluorine, and zinc. And over here you can see what percentage of it is by weight in the human body. Okay, that doesn't mean by amount occurring, because it might actually weigh less, but at least in terms of overall percentage, most of you is actually made up of oxygen. A lot of that has to do with the fact that roughly somewhere between 60 to 70% of you is made up of water, which has the formula H2O. And so that's where you're getting all the oxygen from in your mass. We're certainly going to need carbon. Okay, that's going to be one of the most essential elements. And hydrogen is a lot of that's coming from water. Nitrogen is going to be in amino acids, and then the rest of this stuff is just kind of trace amounts. Now we're looking, under, percent and a half. Calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium. A lot of this stuff you get through your diet in very tiny amounts. Okay, we'll talk about that later. So even though atoms themselves come from a term meaning indivisible, right? We said just a minute ago that atomos meant indivisible. Okay, indivisible, if I can spell, there we go. There are particles smaller than an atom. Okay, there are pieces that make up an atom, and the term for that is subatomic particles. Now, don't let that term scare you or anything. Sub just means smaller than, atomic being the adjective for atom, so subatomic meaning smaller than an atom particles. Okay, things that make up atoms. So, what are those? We have neutrons, which you'll see abbreviated sometimes as just a lowercase n, cursive, italicized. They have no charge. Protons with a italicized P, sometimes with a positive sign. Usually it's written as a superscript like that. They've got a positive charge, and electrons with a lowercase e and a negative sign, oftentimes written as a superscript. These units are so tiny, these subatomic particles are so tiny, they've got their own unit, and we call it AMUs. Okay, an atom is neutral, so we've got this positive charge, right? We've got positively charged protons, and we've got negatively charged electrons. For something to be considered an atom, the number of protons in it needs to equal the number of electrons. The number of positive charges is being canceled out by the number of negative charges. Okay, it's got equal numbers of protons and electrons. Notice, it doesn't matter though about the neutrons, because neutrons don't affect the charge. So we can have varying numbers of neutrons. We'll see here in a minute. Okay, and then so we get to our first term here that we saw just a minute ago, which is mass number, and that is the total number of protons and neutrons in the atom's nucleus. So mass number is going to be protons plus neutrons. All right. Over here in this picture, okay, in our little table over here, for subatomic particles, you can see neutrons have a mass of 1, protons have a mass of 1, electrons are even way tinier than that. They're about 1/2000th or so the size of these other two. Okay, and you can see the charge there. All right. So what does it look like inside of an atom? The protons and neutrons cluster together in the center. Okay, so we get protons and neutrons clustered in the center of this thing, okay, forming the atomic nucleus. All right, so we consider this the nucleus, this bit right here. And then outside of that, okay, in varying directions, okay, and locations, we have electrons moving around. All right. They're in continuous rapid motion around the nucleus within a large three-dimensional space. Okay, so they're moving around the protons and neutrons, which are there in the middle. So you can kind of see down here as a picture of what's going on. Hydrogen has got a single proton in the middle, does not have a neutron, at least most hydrogen does not have a neutron, and a single electron, because we need to have, for every positively charged proton, you need a negatively charged electron to balance that out so that it's electrically neutral. So this is what a hydrogen atom would look like. Single proton, single electron, electrons moving around the outside of this. It's not necessarily a circular path, but for the sake of keeping it consistent and easy to follow, that's oftentimes how it's drawn. Okay, helium is going to be your element number 2, right? If you look at your periodic table, it's going to have 2 protons and 2 neutrons. All right, so kind of what I had drawn up here, actually. Okay, so that's the nucleus, those 4 subatomic particles right there. And because I have 2 protons, I need 2 electrons to balance that out. Okay, the 2 positive charges need 2 negative charges to balance out. And so that's what it would look like. An important thing to note here is what actually defines something as being an atom, I should say, of a particular element. Okay? What defines something of being an atom of a particular element? So for instance, like, what's the difference between the hydrogen atom and the helium atom we saw just a moment ago? All right. The answer is the number of protons. Hydrogen had 1 proton and helium had 2 protons. Okay, that's the difference. All right, if you had a hydrogen nucleus, all right, which is just a single proton, all right, and we add in another proton to that, it no longer behaves as hydrogen. Okay, we just change it from hydrogen to helium. That's actually what the sun's doing. Okay, it's generating helium by fusing together hydrogen nuclei. Anyways, but the number of protons tells you what element there is. So another example here, okay, if we go look at, say, like the next one down the list, okay, lithium. Lithium is element number 3, which means a lithium nucleus has 3 protons. All right. This is called the atomic number. All right, so we would also call the number of protons the atomic number. We can say it's also the number of protons. Okay. So we would say that hydrogen's atomic number is 1, helium's atomic number is 2, lithium's atomic number is 3, okay, beryllium's atomic number is 4, and so on. Okay. Again, so for another example here, oxygen always has 8 protons. Every neon atom always has 10 protons. If you change the number of protons, you've changed the element. Okay, if you manage to remove one of oxygen's 8 protons, it's no longer oxygen, it behaves as nitrogen. That's what we consider it. Well, we've said that atoms need equal numbers of protons and electrons for them to be considered electrically neutral. But what about the number of neutrons? Since they have no charge, how does that play into how many there are? And we saw previously that the hydrogen atom was just a single proton, right? Hydrogen was just 1 proton, and helium, okay, was 2 protons and 2 neutrons. So what gives? Why does hydrogen not have one? Why does helium have some? And what does this actually mean? Well, since only protons determine what the element is, what if there are differing numbers of neutrons? What if we could have helium with 3 neutrons? Would it stay helium? Yeah, because the proton number didn't change. Okay. Atoms of the same element with different numbers of neutrons are called isotopes. This is an important thing. A very common example here is something called carbon-12 and carbon-14. Okay, we'll actually see this later on this year again. Basically what this is right here and what these things are called, they're called carbon-12 and carbon-14. This is the atomic mass, right? And the names there, okay, that's the atomic mass, which means that that is the proton number plus the neutron number, right? Proton number plus the neutron number. Well, if you go find carbon on your table, all right, I'm going to do this down below here because I'm running a little bit out of room. Okay, carbon has 6 protons, no matter what carbon you got, okay? Carbon's got 6 protons. The atomic mass is the proton plus the neutron number, so it's 12. Well, 6 protons plus some number of neutrons gives us a total of 12. Well, you guys are smart enough. 6 plus 6 gives us 12. So that means that carbon-12 has 6 neutrons. And over here, okay, carbon-14, my proton and neutron number need to add up to 14. Well, my proton number can't change, that is 6, but my neutron number can be different. So 6 plus what gives us 14? That should be 8. Okay? We call these isotopes of carbon. They're the same element, carbon-12 and carbon-14. They both behave like carbon. Okay? Chemically, they're still carbon. But the number of neutrons is different. And this is actually important. This one over here is radioactive and decays at a very particular rate. And we can use carbon-14 to actually carbon date stuff is what it's called. We can figure out how old it is by how much carbon-14 there is. Because this disappears over time. It's radioactive. Okay, but these are called isotopes. These are two different isotopes of carbon. So at least the ones that are out there that we know about. Most isotopes are stable, that are naturally occurring. That is, they are not radioactive. Okay, carbon-12 and carbon-14, they're carbon-12 is very stable. Carbon-14 is mostly stable, but it is radioactive. It's very slowly radioactive. If something is radioactive, that means the nuclei spontaneously break apart or decay. Okay, so what ends up happening with carbon-14, okay, which I'm going to write like this, is over time, over long periods of time, okay, it slowly becomes carbon-12. All right, is what it does, is it decays down. This right here is radioactive, which means its nucleus breaks apart. It's losing some neutrons over time. Okay, it went from 8 down to 6. Okay, so this one right here is radioactive. All right, this one right here is stable. Okay, carbon-12 is not going to break down anymore. But that's what actual radioactivity is. When you hear something is radioactive, that means the nucleus is not stable and it breaks apart. So these 6 protons and 8 neutrons of carbon-14 over time degrade down to this. Okay, this is a stable isotope. So we were saying this just a second ago. Okay, when atoms break apart, they emit subatomic particles, protons, neutrons, or electrons. Okay, that carry large amounts of energy. You can't convert one element to another by ordinary chemical reactions, but a radioactive atom, if it emits protons, can change its nature. You may have heard of things like radon gas, okay, which is element 86. All right. Radon gas is radioactive. It's not good for you to breathe it in because it's gas, and then it's radioactive inside of your lungs. But over time, that slowly breaks down into lead, okay, which has 82 protons. So over a series of processes there, it actually loses 4 protons and changes the element that it actually is. Okay, so it's slowly radioactive here, coming down to lead. All right, and we were just saying a minute ago about carbon-12 and carbon-14, right? I don't need to go back over that example. Carbon-14 over time slowly degrades down to carbon-12 by losing 2 neutrons. And how an element is radioactive, or what it does in radioactivity, it varies, okay? Not every single one's going to do the same thing, right? There's an example right here of doing something different than what carbon-12 and carbon-14 were doing. And just so you are aware, some radioactive isotopes damage cells. Basically what happens is these protons, or if you've got an atom here, draw one in, okay, that's radioactive, you've got electrons flying around it, right, okay, going around in a circle. Basically, if little particles start shooting off of this thing, okay, at very high speeds with high energy, whether those are protons or neutrons or electrons or other types of particles, what could end up happening is your DNA, okay, all right, if it gets hit with this stuff, okay, can actually damage it and cause mutations. So basically it gets hit really hard with these radioactive particles, okay, and then you might actually have damage to it. And that's not good, right? Usually over time that ends up with very bad mutations and oftentimes usually cancerous, okay? But that's why, like, why is radiation bad for you? What is radiation poison doing? Basically what's happening is this radiation coming off the radioactive atoms is damaging your DNA, which is not good over long periods of time. It's also the reason why when you go get things like, say, an X-ray, they put a big lead vest on you. Same idea as that the photons of light, in this case not visible light, but the photons of the X-ray hitting your DNA does the same thing. It damages it over time, which again leads to not good things down the road. So let's get into a little bit more detail of what's going on inside of the atom. We have the nucleus, then we've got the electrons going around it. So what's going on here? The nucleus is providing stability. It's resisting outside forces, okay? It's got a lot of mass in the middle. You'll learn more about that in chemistry. But it's very heavy, and it kind of holds the electrons towards it. The electrons react with atoms in the surroundings. It's actually kind of an important point here, okay? Think about it. If I've got an atom here with a nucleus in the middle, okay, and the electrons are going around the outside, when these things go to react, okay, here comes atom number 2, what's actually going to hit the other atoms, right? Electrons, okay? The electrons in here, let me change the color just so that stands out, okay? The electrons in here are what's actually reacting. The electrons from this atom and the electrons from this atom are going to interact with each other. Okay, the protons don't, right? They're shielded. They're in the middle here. But these big, large, what we call electron clouds are actually what react with each other. Okay, electrons are part of the reaction. Protons and neutrons are not. They are in the middle there. So the electrons occupy regions around the nucleus called electron shells. So we call them electron cloud if we're referring to just the general region of where they are. But they have shells that they build outward from the center, which we'll see a picture of here on the next slide. Okay, they're called electron shells. These are depicted as increasingly large concentric rings around the nucleus where electrons travel like planets orbiting the sun. It's an easy way to conceptualize it. Is that actually what's happening in real life? No, it's a little bit more complicated than that. But essentially, you're going to have a nucleus. You're going to have ring number 1, right? Ring number 2, ring number 3, and so on and so forth, all the way out. Okay, is what this is going to look like. You got some concentric circles. Okay. The further away from the nucleus, the more energy the electron needs. So if an electron is all the way out here, okay, this electron has more energy than one that is inside here, okay? Less energy. Okay. It's kind of like climbing a ladder. To move from one step up to the next one, you're going to need to put energy into that electron. You're going to need to put more energy into the electron, a bunch more energy into the electron. Okay, it's kind of like climbing a ladder in terms of energy. There's no like middle rung. You either make it to the next step or you don't. Okay, these things exist in a shell. They don't exist in like a half shell, okay, where they're like, somewhere in the middle here. They're either on it or they're falling back down to these lower energy states is essentially what's happening. Okay, so here we have some depictions of some atoms. All right, carbon, right, is element number 6. Oops, change that back to a pen. And how about one you can read on a white background? So 6. Oxygen has 8. Phosphorus is 15. Calcium has 20, okay, in terms of its atomic number. If you're paying attention to here to how this is set up, so here's my nucleus, right, for carbon. Notice how the electrons arrange themselves here. The first shell, okay, this is what we're going to call the first shell, right? Innermost shell, okay? First shell, all right, has 2 electrons. And notice that's the case with all of these things, isn't it? Okay, if I come all the way over here, right? The innermost shell always has 2 electrons, okay? Change back to a color you can see on blue, right? So we'll say the innermost shell has a maximum of 2 electrons, right? Because you're probably wondering, well, Mr. Doyle, what about like hydrogen, right? Hydrogen is just a single proton and a single electron, okay? This first shell can hold a maximum of 2, all right? So when you get to something like hydrogen, or helium, which has got 2 protons, right, and 2 electrons, okay, that second electron still in that innermost shell. But then when you get up to the next one, which is lithium, which has 3 protons and 3 electrons, okay, the first 2 electrons are going in the first shell, and then there's no more room. Whoops, that's a horrible circle. Let's try that again. Okay, the next electron's got to move out to the next shell. And then you'll notice there's actually kind of a repeating pattern after that. Okay, if we come back here for a moment. All right. Each shell after the first shell, okay, has a max of 8 electrons. Okay, so here on the first one, carbon, you'll notice has 4, right? And they're equally spread out. Okay, if we look here on oxygen, all right, we've got 2, 4, 5, 6 in the second shell. Okay, and then we had the 2 in the original shell, so that's how we end up still with 8, right? Okay, and this last one here, phosphorus, at least not the last one, but this one, next one, right, we've got in the next shell out, we've got 2, 4, 6, 8. Okay, and notice that it has a maximum of 15. So it had 2 in the first shell, 8, which would give it a total of 10, which means the next 5 actually are going in the shell after that. So notice, after the first shell, at least for our purposes in biology class, we have a maximum of 8 electrons. The inner one holds 2, and then everyone after that holds a maximum of 8. Okay, and then we've got here calcium, right? It's got 2 in the middle, 8, another 8, and then 2 more. Okay, there's actually a special way that these electrons pair up together, but we'll talk about that more later on. Okay, so let's just try this together real quickly. How many electrons are in the outermost shell of Na is sodium? So if you go find sodium on the table, it's got an atomic number of 11, which means if it's a neutral atom, it's going to have 11 electrons. So we need 11 total. The first 2, right, should be going in the innermost shell. So if we subtract 2 off that, right, now we're down to 9. Okay. Every shell after that first shell can hold a maximum of 8. Okay, so that's going to have 1, 2, 3, 4, 5, 6, 7, 8. And notice how I drew them. I drew them in pairs. Okay, and I drew them in pairs after I had drawn each one separate. We'll learn more about that here later on, but that's okay for right now. Meaning I have 1 left. So the last electron, okay, goes in the outermost shell. And so if the question says how many electrons are in the outermost shell of sodium, all right, it's going to be 1. Right, 1 is going to be the answer here because we filled up all of the inner shells, okay, with the previous 10. All right. Let's go ahead and have you try this last one. How many electrons are in the outermost shell of silicon's element Si? You've got to find it on the table and figure out how many there are, and then do the similar process that we were doing up here, okay, figuring out which electrons go into which shell.